Okay, so we're going to start our discussion about design patterns, and this is one of the things that you can't really have a software engineering course that doesn't talk about them. But one of the holy grails of software engineering is to be able to reuse stuff, and design patterns give us one of several ways to do that. So rather than just presenting a big catalog laundry list of design patterns, what we tried to do in preparing this material is to actually start from anti-patterns. An anti-pattern is something that looks like it could use a better solution than it has, and you're not quite sure why. And there's a set of guidelines that came out of the Agile and refactoring community that go by the acronym of SOLID. So we're going to sort of treat those guidelines in conjunction with design patterns, because there's sort of a connection between places where your code is not obeying the guidelines and places where your code could benefit from the application of design patterns. So design patterns actually came out of the architecture world originally, like the actual architecture for buildings, right? Not software architecture. Christopher Alexander wrote in his landmark book, A Pattern Language, in 1977, that a pattern describes a problem that occurs often along with a tried solution. So the idea is that not every instance of the problem is identical, but you have instances of the problem that look enough like each other that you try to find solutions that could sort of be readily repurposed for the new problem instances. And he did this in the context of civil architecture, architecture for cities, like buildings that people live and work in. He observed that there were some patterns that actually could be used at different scales, whether you were talking about sort of a small town to much larger cities. So a pattern language is sort of an organized way of collecting these things. And it's a little bit confusing, at least when I learned about design patterns, to talk about a pattern language, because when I think of a language, I think of a precisely specified language, like a computer programming language. Really, it's more like a vocabulary for talking about things. And if you have any background in the design world, when designers talk about a design language for a family of products, they really mean a sort of set of underlying concepts or design motifs that can be used across the product range. So think of it more sort of in those terms. And both in the design patterns outside of and inside of computer science, the goal is pretty simple. It's a way to separate the things that change from the things that stay the same. And there's two reasons you want to do this. One of them is obviously the things that don't change, you could reuse those elements in other problems and save yourself some work. And by separating out the minimal set of things that do have to change, you're minimizing the cost of change because you know exactly where the change has to take place. So that's the idea. And in software, actually, patterns occur all over the place besides the ones that we're going to talk about. There's what some people call architectural or macro scale patterns, where you sort of zoom out and look at the gross structure of the software from far away. So things like model view controller are an example of this. Or the pipe and filter pattern, which a lot of people think of in terms of like the Unix pipelines, when you can connect commands together and the output of one command becomes the processing input for the next command. Event-based, we actually already saw that you can think of JavaScript as implementing the event-based design pattern, where events just sort of happen and you've got to declare which code captures the different event types. There's also patterns of computation. So there's sort of different kinds of mathematical computations that occur in a variety of scientific applications. Fourier transforms for doing signal processing, linear algebra in various forms. We're going to talk about the gang of four patterns, which really have to do with software structure below the level of gross architecture. And these are patterns that are called, they're subdivided into structural, creational, and behavior patterns according to what part of the object lifecycle they participate in. So the gang of four wrote I guess the canonical design patterns book. On my small screen, I can no longer read all their names, but Gamma, Johnson, somebody, and somebody. Huh?
Gamma, Helm, Johnson, Visselli.
Right. Well, see, the thing is, most people don't use the canonical book anymore, because since then, the examples in the book not only have been sort of retrofitted to address the needs of other languages. I think the original set of examples were mostly in C++ or possibly in Java. I can't remember. But they tried to capture some common patterns in terms of communicating objects and classes. And they were looking for common solutions to problems that came up over and over again. They originally came up with a catalog of the gang of four patterns. There's 23 of them. And since that time, other people have sort of unofficially added to that catalog. So the thing to remember is that a pattern is not something that is expressed directly in a rigorous programming language. It's not usually even provided as a library or a set of classes, although sometimes elements of patterns can be. But it's more like a blueprint for a design that you could easily adapt to solve other similar problems. So this is the original 23 patterns, not all of which we're going to cover, happily. But we're actually going to talk about at least a couple from each of these three general categories. There's a handful of patterns that have to do with creating different types of objects or instantiating classes. There's a bunch of patterns that have to do with structure. In other words, how do different classes interact with each other? What are some different relationships among them? And then there's behavioral patterns, which is how do you do certain operations on elements of those classes. So the ones that are in boldface are some of the ones that we're going to talk about, and we're going to sort of consider them in clumps alongside of an example of when you would want to use them. The way we're going to illustrate when you want to use them is we're going to use the concept of an anti-pattern. And I'll pause for a moment here to recommend a book I really like, and I have no financial interest in, but it's called Rails Anti-Patterns. And really, it's a book that shows a bunch of well-intentioned code that grew a little too big to still have a good design while meeting the customer need. So even though the code as originally written was good, over the sort of natural evolution of adding functionality, it became messy. And it started to exhibit an anti-pattern, meaning it got to a point where you would look at it and say, wait a minute, why aren't they following the XYZ design pattern, which clearly tries to solve this problem? And the answer is that that's not the code they wrote in the first place. It sort of evolved to that place through accreting complexity over time. A term that you'll hear in industry about this is technical debt. Technical debt is what happens when you know you need to make a modification to something. You're kind of looking at it and thinking, you know, I think the right way to do this is to refactor the code to have this other structure. And if I did that, it would be easy to make this change. But I don't have time to do that because, oh my God, they need this feature like next week. So I'm just going to do the quick and dirty thing, which I know is wrong, and I know it makes the code ugly, but I'll come back and fix it later and refactor it. World's biggest lies, number 37. So that's called technical debt. And when you accumulate, we're not going to go through 1 through 36. The technical debt is what you accumulate when you consciously make those trade-offs. And if you get to a certain point of technical debt accumulation, you start sprouting anti-patterns in your code. The way you can tell if you're doing this, first of all, most of the time you know you're doing it. That's why it's technical debt, because you know you're incurring it. But if you're looking at your code and you see symptoms like viscosity, which is you know what the right thing is, but the way your code is structured, it's actually less work for you to do the hacky thing. Immobility is similar. There's a piece of functionality that you know is replicated at various places. You'd like to dry it out, but because it's so tightly woven into all the places it's used, it's actually pretty difficult to factor it out and use it. That's called immobility. Related to that is needless repetition. Because you can't factor it out and make it reusable, you end up copying and pasting many places, which is the wrong thing to do. And needless complexity from generality. So somewhere that you thought you'd need generality, you put in a bunch of complexity to handle the general case. You actually never needed to use the general case, and now you're stuck with a complexity anyway. So these are all symptoms that you might be able to refactor your code to use a design pattern or more than one design pattern and improve the structure all around. We're going to look at design patterns in the context of this great acronym that comes from one of the co-authors of the Agile Manifesto called SOLID. And SOLID is a set of guidelines for minimizing the cost of change in a non-trivial piece of software where you have many classes interacting with each other. So one by one, we're going to talk about the single responsibility principle, the open-closed principle, Liskov's substitution principle, named for a Turing Award winner, the dependency injection principle, which I have labeled as injection of dependencies because it makes the acronym come out, and the Demeter principle. Now, traditionally, when you read about SOLID in most other books, the I is used for the interface segregation principle. There's a quick explanation in our book of why that principle doesn't really arise so much in Ruby. So we decided to hijack the I and instead use it for injection of dependencies. And that lets us use D for the Demeter principle, which is sort of an add-on to SOLID that came later, but it's at least as important in our view, and it actually fits well with the other four. So that's our version of SOLID. Without going through this table in detail, what I want to point out is that there's direct correspondences between what we're doing with design patterns and what we already did with things like method-level refactoring and SOFA. So within a class, we talked about looking for code smells within a method. There were lists of code smells that you could sort of check against. There were different metrics that you could quantitatively see if your code was running into trouble. You could refactor by moving code from one method to another. And we had this set of guidelines called SOFA that sort of summed up some of these best practices. Similarly, for classes, we're going to also look for smells, but now we're going to call them design smells because they're not necessarily about the individual lines of code. They're more about how different classes interoperate with each other, the sort of structure of class collaboration. And again, there's catalogs of both design smells and design patterns that you could use to overcome them. What we'll see is that just as some refactorings of code aren't necessary in Ruby, there is also some design patterns that don't arise because Ruby makes it easier to avoid the pitfalls. Just as with method-level metrics, there are metrics that help you assess whether you're in violation of or possible violation of a design smell. We can refactor not just by moving code among methods, but by moving code from one class to another, or by creating a new class to extract some stuff that really doesn't belong in the place that it lives now. And we have another helpful acronym. So now we'll have SOFA and solid, and make of those what you will. So let's warm up for our design patterns discussion by speculating on which statement is false. Software that uses more design patterns isn't necessarily better. So using more patterns doesn't necessarily guarantee you're doing a better job. Well-designed software can still evolve to the point where patterns become anti-patterns. Trying to apply design patterns too early can be just as bad as too late. And most design patterns are specific to a particular subset of programming languages. So what is the best answer for which one statement is false?